Relational structures are the foundation of modern data systems, even if most people never see them directly. At their core, relational structures organize data into tables, with rows representing entities and columns representing attributes. Imagine a spreadsheet where each sheet describes a kind of thing: customers, products, orders. That is the intuitive starting point. What makes relational structures powerful is not the table itself, but the relationships between tables, expressed with keys and references. A primary key uniquely identifies each row in a table and gives us a stable handle on an entity. A foreign key is a value in one table that points to a primary key in another table, establishing a relationship. Those relationships let us model one-to-one, one-to-many, and many-to-many associations cleanly and precisely. For example, one customer can place many orders, which is a classic one-to-many relationship that relational tables express naturally. Many-to-many relationships are handled by introducing a join table that links the two entities together. That join table itself is a first-class relational table with its own keys and constraints. Relational design encourages normalization, a set of principles that reduce duplication and enforce consistency. Normal forms, from first to third and beyond, guide how we split data into tables to prevent anomalies. Without normalization, updates become risky because the same fact is stored in many places and can get out of sync. Duplicate data leads to update anomalies, deletion anomalies, and insertion anomalies that compromise integrity. When we follow normalization rules, we separate concerns. Each table captures one concept or entity type. Referential integrity is the rule set that ensures foreign keys actually point to existing primary keys. Databases enforce referential integrity using constraints so that relationships cannot be broken accidentally. Transactions provide atomicity, consistency, isolation, and durability, the ACID properties that make relational systems reliable. Atomicity means a set of related changes, either all succeed or all fail, which prevents partial updates from corrupting the system. Isolation ensures concurrent transactions behave as if they were run serially, avoiding race conditions and lost updates. Durability guarantees that once a transaction is committed, its changes persist despite crashes or power loss. These guarantees, combined with relational structure, are why relational databases are popular for critical systems. Relational schemas are explicit contracts between data producers and consumers, which reduces ambiguity across teams. When you design a schema, you define types, nullability, default values, and relationships that downstream tools can rely on. Good schema design also considers indexing strategies to make queries efficient and predictable. Indexes accelerate lookup, sort, and join operations by allowing the database to find rows without scanning whole tables. Choosing the right index depends on query patterns. Single column indexes, composite indexes, and covering indexes each have roles. Bad indexing choices can slow writes dramatically or make reads still expensive if the index doesn't match query predicates. Joins are the essential operation that reconnects normalized data across tables during queries. A join combines rows from two or more tables based on matching key values, and it is the mechanism that reconstructs complex objects. There are different join types: inner, left, right, and full, each describing how unmatched rows are handled. Inner joins return only matching rows, while outer joins preserve unmatched rows on one or both sides. Understanding join semantics is critical because the same data can yield very different results depending on the join used. Relational algebra, the theoretical underpinning of these operations, guarantees that queries can be expressed and optimized mathematically. Query planners in modern databases rewrite and optimize SQL into efficient execution plans using indices and join orders. Normalized schemas make many operations safe and consistent, but they can increase the number of joins necessary for common queries. In read-heavy systems, designers often denormalize selectively to reduce join costs and improve performance. Denormalization trades redundancy for speed, and it introduces the need for additional logic to keep duplicated data consistent. Practical database design blends normalization and denormalization based on access patterns and consistency requirements. Another core benefit of relational structures is their maturity. Decades of research, tooling, and operational experience exist around them. Technologies like SQL, transaction logs, materialized views, and sophisticated backup tools are the product of that ecosystem. Relational schemas also support strong data governance because constraints, types, and access controls are explicit and enforceable. Permissions can be applied at table, row, or column level to protect sensitive attributes while allowing broad access to general data. For analysts and data scientists, structured relational data is often easier to reason about and integrate into pipelines. Yet relational structures are not a silver bullet. They have limitations that drive alternative models in certain domains. Hierarchical, document, key value, and graph databases each solve problems that are awkward in relational schemas. Document stores, for example, allow nested, schemaless records that are convenient for rapidly evolving applications. Graph databases excel when relationships are first-class citizens and traversals are deep and frequent. Still, many systems combine models, using relational databases where integrity and transactions are essential, and other stores for flexibility or scale. Designing relational schemas begins with domain modeling. Identify entities, attributes, and the cardinality of relationships. A common pattern is to start with an entity relationship diagram that captures entities and their associations visually. Once the ER model is stable, translate entities to tables, attributes to columns, and relationships to foreign keys or join tables. Choose appropriate types for columns to represent units and precision explicitly, avoiding ambiguity between meters and feet or cents and dollars. Failing to encode units and types can lead to subtle bugs that are hard to detect in production. Handle optionality explicitly by using nullable columns or separate association tables when a relationship is truly optional. For many-to-many relationships, create associative tables that may also capture relationship attributes like quantity or timestamp. Consider natural keys versus surrogate keys. Natural keys encode domain meaning, while surrogate keys are synthetic identifiers used for simplicity. Surrogate keys are often preferred for stability and performance, but natural keys can provide a useful uniqueness constraint for business logic. You should document which key is canonical for business purposes, so future changes remain consistent. Schema evolution is inevitable, so adopt patterns that minimize breaking changes, additive changes, default values, and careful migrations. Breaking changes that rename or remove columns can surprise downstream consumers and cause failures in production. Migrations should be automated, tested, and rolled out gradually with monitoring for unexpected data or performance regressions. Backup and recovery strategies are essential. Relational systems often use point-in-time recovery and write-ahead logs to restore correct state. Replication helps with availability and read scaling, but it also introduces eventual consistency challenges that designers must understand. In synchronous replication, latency increases, but consistency is stronger. In asynchronous replication, performance improves, but replicas may lag. For high-scale workloads, sharding partitions tables across nodes by a key to distribute load and storage. Sharding complicates cross-shard joins and transactions, so the partition key must be chosen with care. Observability is another structural concern. Capture schema change events, migration history, and validation failures in logs and dashboards. Schema registries and data catalogs help teams discover table definitions, column meanings, and lineage for safe reuse. Testing at the data level. Unit tests for constraints, integration tests for migrations, and property-based tests for invariants reduces surprises in production. Performance tuning requires measuring query plans, index usage, and hotspots rather than guessing where bottlenecks are. Real-world examples make these ideas concrete. A customer table, an orders table, and an order items table form a classic normalized design. The order items table captures the many-to-many relationship between orders and products while preserving quantity and price at the time of sale. Reporting queries reconstruct invoices by joining these tables and aggregating totals, which demonstrates how joins rebuild complex objects. If reporting demands become too slow, denormalized reporting tables or materialized views can store pre-computed results for fast reads. Finally, think about governance and ethics. Schemas should include provenance, source identifiers, and clear descriptions to avoid misuse of data. Relational structures are tools that let teams build reliable, auditable, and maintainable systems when used intentionally. If you are new to database design, start small, model your domain, enforce basic constraints, and iterate with real usage. Over time, you will learn when to normalize for correctness and when to denormalize for performance, guided by actual workloads. In the end, relational structures are less about tables and more about expressing relationships, constraints, and the guarantees systems need to operate safely. When you design those structures consciously, your software becomes easier to reason about, more robust under failure, and more trustworthy for everyone who depends on it.